Alright, student, let us start today's topic, that is matrices. Again, I would say it is a very interesting topic as per se your IIT JEE Main syllabus as well, because again it is one of those topics which is really scoring. So if you know the chapter entirely in and out, all the things that are related to this particular chapter, the 4 marks is a short for you. So 4 marks is for matrices and 4 marks is for determinants. So that is the reason matrices and determinants fetch at least 8 marks. So which is a very high priority for this particular chapter. All right. So that is why we are giving complete focus a day to matrices and a day to determinants, because they are actually of that importance. The syllabus that we are going to cover in today's video will be basics on the types of matrices, trace of a matrix, algebra, multiplication, transpose, symmetric and skew-symmetric. We do also have something called Hermitian and skew-Hermitian matrices, but we'll not be getting into it because it is outside the scope of JEE Mains. Determinant of a matrix, adjoint, inverse, system of linear equations, and this is completely a topic which I have taken specifically for both the boards level. People who are preparing for both. So this is something for the boards, elementary row transformation using finding inverse using elementary row or column transformation. All right, so let's start the chapter. Okay, let us start quickly with the basics. So what do you mean by a matrix? So matrix is nothing but when your numbers, or you can say elements, right? Elements, numbers, this could be anything, right? That is why I'm saying elements, numbers, alphabets, any quantity are written in a pattern of rows and columns, right? They are written into rows plus columns. So this is basically what is a matrix. So it is basically just representation. Okay, so if I talk about matrices, it does not have physical significance. It is just representation, that how you write numbers. So anything written in a square box in rows and columns. So 1, 2, 3, 4 and so on. So I can go on writing numbers and I can then add A, B, C and D. So this is not a mathematical tool. So it need not be that every number will be a number or every digit should be alphabet. You can write anything. So how do we say that is? It has 3 rows, first row, second row and third row, and first column, second column, third column and fourth column. So it is called 3 cross 4 matrix, that is number of rows into number of columns. This particular quantity over that is written here is known as the order of the matrix. Order is nothing but number of rows multiplied by number of columns. This is how you actually write. Okay, so I should not say equal, it is again a syntax how you write. So number of columns. Okay, I know that everybody knows this step. It is just to start the chapter on the basic front. Okay, why it is chapter important? So people who are into computer science must have done this, right? So in computer science, the application is huge because it is used to store numbers and take variable in and out of it. So this is basically nothing but 2D array that you can compare, right? Arrays, if you people have done. Okay. So let's take a very basic problem which I can start with. Find the number of matrices having 12 elements. So let's say number of rows is m, number of columns is n. So number of elements. So this is represents number of elements, right? This represents number of elements. So this is given to be number of elements is 12. That means m into n is given to be 12 here. So now you need to find how many number of matrices are possible. So that means you need to find different values or different pairs of m and n which will satisfy this. So the answers that we could have here will be, let's say 1 and 12, right? And we can also swap them. So 1 comma 12. So this means 1 row and 12 columns. That is something written as a horizontal line. This is 12 rows, 1 column. Similarly, what you could have said 2 into 6, that is 2 comma 6 order, and this could order be 6 comma 2, 3 comma 4 order, and this could be 4 comma 3 order. Anything left that I have not taken? Yes. So these are the different order matrices that you people can get. So the answer is that you can have 6 different type of matrices, 6 different matrices which can be formed using 12 elements. All right. Okay, now let's quickly do the other definitions, or in fact the type of matrices that are there. So first is the row matrix. As the name suggests, the number of row will be fixed here. So here m is nothing but 1 and n can take any value. I should not say r positive. In fact, I should say n should belong to a natural number, right? Then only it makes sense. So you can write like this. So column matrix, as the name suggests, so it will be a vertical matrix, right? Vertical matrix where n will be equal to 1 and m can take any natural value. Okay, square matrices that we have to study in great depth here, where m is equal to n. As the name suggests, square, the length and the breadth should be equal, so number of rows and number of columns should be equal. Diagonal matrix, a special case of square matrices, where all the elements, so for this, let me just have this particular matrix here. So I have taken a matrix which I do not know the order. Let's say m cross n is the order. So, but yes, so you cannot say m cross n here, because for diagonal, so all these three are basically subset of square matrices. So for diagonal matrices, it should be a square matrix. So if you say m cross n, then I know that m is equal to n, or I can straight away say m cross m or n cross n, whatever you want to say. So for diagonal matrices, what is the condition? That all non-diagonal elements should be 0. All non-diagonal. So what do you understand by non-diagonal? So how do you represent non-diagonals in the syntax form? So all non-diagonal elements should be 0. So for non-diagonal elements, you will write aij. So this is the each element of the matrix, right? So any element of a matrix can be denoted like this, aij, where you just put the value of I represents the number row, right, and j represents the jth column, right. This is what is meant by here. So if this has to be equal to 0 when non-diagonal, so non-diagonal is written like I is not equal to j, because if you take the diagonal elements like this and the other ones, so if you notice there, every element which lies on the diagonal, so I1 1 1 2 2 3 3, so they have I is equal to j. In fact, if you see the matrix, there are if you talk about the square matrices, so people are confused that, sir, there could be two diagonals, right? There could be two diagonals, right? Clear? So one is this way and the other could start from somewhere here also, right? So but this particular blue diagonal is called the primary diagonal, and which is what we are interested in. This is called the primary diagonal, right? Primary diagonal, which is basically the diagonal of a matrix, and it starts, remember, it starts from a1 element, that is row 1 column 1 element. So it will start from here. Okay, and also importantly, interestingly some questions have been asked for non-diagonals. So I have said non-diagonal element 0. I have not talked about the diagonal element. So it might be possible that aii could be 0 or could not be equal to 0. I'm not sure. Both of them can be true for diagonal elements. So for example, if you get something like this 1 0 0 0 0 0 and 0 0 3, so I will call this as a diagonal element. Why? Because I do not have to look at the elements which fall in this line. I have to see at the remaining element 0 0 0 0 0 0. So this satisfies the condition of diagonal. Do not look at the diagonal entities for the condition. Okay, this is what is meant by this. Scalar matrix is a special case of you can say it's a special case of diagonal matrix, right, where this has to be the condition that aij is equal to 0 when I is not equal to j, and also aii is always a same value, right? It has the same value. It has same value. So 1 0 3, they are three different numbers, so the diagonal will have same number. So for example, 1 is written here, so 1 here should be here, then the other third element of the row should also be 1. This is the scalar, right? And the other interesting thing about the diagonal elements is that you can write them in a very short form, that is diag, which is very commonly used. So diag a1 a2 a3 up till an. So what do you mean by this is you just have written the diagonal elements, other will be 0. So for example, if you want to write this particular step, this particular matrix, you can write as diagonal 1 comma 1 comma 1. For this you can write diagonal 1 0 3, right? This is how you can represent diagonal matrices also. But for scalar, the diagonal elements must be same. Identity matrix, another special case of scalar, right, where the diagonal elements are all equal to 1, constant, right? And it's a very important thing in matrices, because we represent that with capital I, where capital I is nothing but when the diagonal elements are 1. Okay. And the other two type of matrices that we have to also cover is upper triangular matrix and lower triangular matrix. And as the name suggests, what they mean is, so let me take let's say A, B, C, D, E, F, G, H, I. So this is a 3 cross 3 matrix, right? 3 cross 3. So for upper triangular matrix, so triangle can be, see, if this is a line, so it divides the square into two regions, upper region and the lower region. So the upper triangular matrix So for upper triangular matrix, the elements that will be considered will be B, C, F. So these lie in the upper triangular matrices. So for upper triangular matrices, all the elements below the primary diagonal. So elements below the diagonal, must be 0. This is what is meant by this. So for here, if I talk about D, G, H, they all should be equal to 0. This is what is meant by upper triangular matrix. And similarly for lower triangular matrices, elements above the diagonal, right, upward to diagonal must be 0, right? So what are those elements? That is B should C and F, they should be all equal to 0 for lower triangular matrix to exist. So something, for example, would be 1, 2, 3. This will be 0. This can be 3. This can be 5, 0, 0, and 7. So this is an example of upper triangular matrices where the elements below the diagonal are 0, right? This is what is meant by upper triangular matrix. And how do we write that mathematically is that if we talk about upper triangular matrices, so Aij will be equal to 0 when I is greater than j. So if you talk about I greater than j, all those elements which are below the diagonal will be the cases. So for example, if I take this here, this element is A21, this element is A31, this element is A32, and this element is, we don't talk about this element, right, at all. So if you take all these three elements, can you see that the value of I is greater than the value of j? That is why I'm saying this. For this, what you people will be right the opposite. So Aij will be equal to 0 when I is less than j. So if I is less than j, then you will get the elements which are, yes, above the diagonal. This is how you will take upper triangular and lower triangular matrices. Let's take a simple question on this. Find minimum number of zeros in an upper triangular matrix or a lower triangular matrix of order n, right? So let us take this case. So this is, let's say, is n cross n matrix is there. So this is the first row, right? The first row cannot have any 0 as per the condition. So let's say we are trying to form upper triangular matrix, right? Upper triangular matrix. For upper triangular matrix, the condition is Aij should be equal to 0 whenever I is greater than j. So that means the first element that must be 0 is this particular element. So in the second row, this is the second row, right? In second row, how many zeros? Minimum number of zeros. That is what we are trying to. In the first row, it is not necessary that there should be any 0. But in the second, yes, it is 1. In the third, right? So in third, there are 2 zeros. Can you see that this is 1, this is 1. In the fourth, there are 3. So this is 3. And by symmetry, in the nth row, then would be n minus 1. So if you just want to add them, so this will be 1 plus 2 plus 3 up till n minus 1. Right? So this is nothing but sum of first n minus 1 natural numbers. And we know the formula for this. It is nothing but n into n minus 1 by 2. Right? This is the answer that we were looking for. So these are the minimum number of zeros that should be there. So why I am saying minimum number of zeros, let's just talk about that also. Minimum number of zeros. So for minimum number of zeros, that means the non-diagonal, the elements which are below the diagonal must be 0, right? Below the diagonal. But nowhere it is mentioned that what about the elements which are above the diagonal, right? So for example, this A2 here can also be 0. This A3 can also be 0. This A4 can also be 0. I am not sure. So that is why we do not talk about this, because this could be various other cases. So but yes, the minimum number of zeros for this to be a upper triangular matrix would be n into n minus 1 by 2. And the same answer would be there for lower triangular matrices, because the same thing would happen for the upper triangle. Alright. Okay, now let's do another important definition, that is sum of diagonal elements of a square matrix A is called the trace. So what do you mean by trace? Let me show you with an example. So first of all, it has to be a square matrix, right? So let's say this is 4, 1, 3 and this is 5, 6 and 2, right? So what are the diagonal elements? Can you tell me the diagonal elements here? So diagonal elements are here nothing but 1, 1 and 2. What is the sum of the diagonal elements? Sum is 4, and this is called the trace of the matrix. So trace is nothing but the sum of the diagonal elements, whatever the order is. So for this, just remember that it has to be a square matrix before you start finding the trace of a particular matrix. Okay, now let's start the algebra of matrices, and I'm going to straight away talk about the questions and skip the properties which you people have already done. And if you was just want to revise quickly, so if you want to add A plus B where A and B are matrices, so they must be comparable matrices, right? So what do you mean by comparable matrices? That their order must be same, right? Order should be same for both of them, then only we can add or subtract them, right? This is the basic property of the uh, uh, addition. And if you want to take something common, so remember, if you want to take common out of a matrix, so common is taken from all elements. That is very important. So this is in fact the differentiation between a matrix and a determinant. So from all elements the common is taken, not from a row or column. So a common is not taken from a row or a column. This is property is valid in terms of determinants. When we'll talk about determinants, this is valid. But if we are taking common from a matrix, so in matrix you have to take column common from each and every element. So let's take the first question. It is said that A is this and B is this. If A is equal to B, you want to find theta. That means if two matrices are equal, A is equal to B, that means their order is equal. First of all, order is equal, and what are equal? All respective elements, right? What do you mean by respective elements? Elements at the same position must be equal. So you want to find theta, so the quick answer is that you can say it's a sine theta. The first element over here should be equal to first element over here, which is 1 by root 2, and this particular answer gives you theta is equal to pi by 4, and you happily come along the examination room thinking that you have fetched the 4 marks, and you talk to your friend that, yeah, what a simple question it was being asked. So but this answer is wrong, right? Just do not do this error. Why? Because I said all respective elements are equal, respective elements, and this is all respective elements. So yes, this is completely fine. If you check about this particular case here, so this should also be equal, which says cos theta now should be equal to minus 1 by root 2. Now if you put theta is equal to pi by 4, this will not satisfy this particular condition. Whereas that if cos theta is negative, this means theta lies in the second quadrant, right? If it lies in the second quadrant, then the value of theta will be what? 3 pi by 4. If you put sine 3 pi by 4, this will still give you 1 by root 2. So the correct answer that we were looking for here is 3 pi by 4. So don't do this silly error for these simple kind of questions. Okay, mind it. Okay, now let's talk about the multiplication of matrices, which is the most important topic of this particular chapter. So let's say A is a matrix, okay, whose order is, let's say, m cross n, right? So it is an order of m cross n. So how it could be written as? A could be written as Aij m cross n, right? And if you want to multiply with a matrix B, right, whose order is, let's say, P cross Q, right? So if it is P cross Q, then this is how we actually write this, the syntax of matrix Bij is equal to P cross Q, right? So if you want to multiply and write AB, right, this is what you want to do, A into B. So the basic minimum condition that should be here is that n should be equal to your P. That is, the number of columns of the first matrix should be equal to number of rows of the second, right? This is the basic stuff. I hope you people will be knowing this. So then what it is that we get here is the C matrix. Let's say we are talking about C. So C can be written as, so this is the mathematical definition of C, Cij, where each element of C can be written as Cij is equal to summation of k going from 1 to P or n, whatever, Aik Bkj, right? K here and K here, right? So do not get confused. I've seen what I did in my class one day, that I wrote this particular stuff and asked a question on this, and the student were puzzled, sir, what is this? So this is how basically we say matrix multiplication in terms of mathematics. There is multiple matrix multiplication formula basically, and this is how we use that in coding as well. So all the elements, so here I will take all the values which should be there, and J will take all the values ranging from 1 to Q, and this will take values ranging from 1 to M. And if somebody asks you, sir, what is the final order, then C order would be nothing but the remaining two elements, that is M and Q. So the order of C will be nothing but M cross Q. This is the order of the final thing that you will get. Okay, so for your example, I've taken two matrices. So the order of this is 3 cross 3 and the order is 3 cross 2. So are they first of all able to be multiplied? Yes. Why? Because 3 here is equal to the number of rows here. So yes, you can multiply and the answer that you people will eventually get will be of 3 cross 2, that is the remaining two elements. That means 3 rows and 2 columns. And how we'll do it, let's see. I make you sure that you understand that stuff. So it is, you multiply a1 with this. So just go over here. So put the value of I as 1, j as 1. So it will be ai11 b11. So this is a1 b1. Then you multiply the second element over here with second element of column 1, right? See here, k will remain now 2 1, right? So and you add them up, that is a2 b3 plus a3 b3. Oh sorry, b5, not b3, it will be b5, right? Because yeah, it's 5 here. So now I hope you have understood, and we just revise how the matrix multiplication is being done. I quickly just go over and do the remaining. So it will be a4 b1, same process, right? So similarly it will be a4 b1 plus this will be what, a5 b3 and plus a6 b5. Similarly the third element would be what, a7 b1 a8 b3 plus a9 b5. And let's talk about the other column also, because there has to be two columns. So then you will say a1 b2 plus a2 b4 plus a3 b6, right? And you can then remainingly do the same stuff right here also. So this is how we do matrix multiplication. So just be careful that the number of columns of the first should be equal to number of columns of the number of rows of the second. Let's talk about the properties of matrix of multiplication, which is I think very important. So first important property that you people have to understand is it is not always commutative, which you people have already done, I suppose. That means AB is not always equal to BA. So we cannot say that AB is equal to BA, right? The swapping, if you do the swapping, so it might not be possible to even multiply. So for example, if I take, let's say A has the order 3 cross 2 and B has the order of 2 cross 7, let's say. So the resultant that you will be expecting is 2 cross 7, which is valid over here. But if I swap both of them, so let's say B becomes 2 cross 7 and A remains still 3 cross 2, so they are not even in the form which can be multiplied. Why? Because here the number of columns and number of rows do not match. So swapping is not valid, a very simple case. They are associative, so that means ABC is written, so anyway you can put the bracket. They are distributive, simple property again, no problems. If you multiply with the identity matrix, so identity matrix could be, when I say IN, so that means order is n, right? I suppose this you people must be knowing, right? So multiplying with the identity matrix does not change the matrices, so matrix remain the same. Multiplication by a null matrix, so what do you mean by a null matrix here? We skipped this in the type of matrices when we did earlier. So null matrix is nothing but when all the elements are 0. All elements are 0. All elements 0. And the very important stuff about null matrices and the identity matrix is that if you are multiplying them and you are not mentioning the order. So for example, I don't write something here, the order, right? Say n here. So it automatically takes the order for which it becomes multiplicable with A, right? So for example, A is 3 cross 3 here. So I will automatically be nothing but 3 cross 3. Don't worry about this. It will automatically take that particular role. If we talk about this another important property here. So if we take the other property, it says if AB is equal to AC. So something that you people have to understand here, that if you have solved and you come out that AB is equal to AC, then never cancel A on both sides and say that B is equal to C. This is not valid. This may or may not be true, right? So you cannot say something like this. Whereas if you know that B is equal to C, the vice versa is true, then you can pre-multiply with A. That is not a problem. That you can do, right? This is not a problem. But going from here to here is allowed. Coming from here to here is not possible. You will not say this. Okay, be very clear about this. And if AB is equal to 0, so for example in algebra what we have done is that if AB comes out to be 0, what we used to say, either A is equal to 0 or B is equal to 0. We cannot say this in the case of matrices. So if two matrices are multiplied and you get a null matrix here, so it is not necessary that either A will be a null matrix or either B will be a null matrix. We cannot say the product of two null matrices can be a null matrix. A simple example for your understanding is that take this as A, right, and take this as B. So if you multiply them, you will get a null matrix, whereas both of them are not null matrices, right? So basic example. Trace of A into B is nothing but trace of B into A. That is possible if if AB and BA are multiplicable, right? They can be multiplied. That's the basic stuff, right? They are multiplicable. Okay. The other important property is multiplication of two diagonal matrices, again a diagonal matrix. Multiplication of two triangular matrices, again a triangular matrix. Multiplication of scalar matrix is also will give you scalar matrix. So the property remains the same. This way you can remember them. So yes, before we go to the question straight away, let's figure out some other important properties of multiplication. So if A and B are two matrices of the same order, so what will you call A plus B whole square, right? So A plus B whole square, generally I have seen students writing something like this: A square plus B square plus 2AB. This formula is valid in terms of algebra but not in terms of matrices. For matrices, what you people will have to do is that you will have to write A square plus B square plus AB plus BA. This is what you people have to do, right? We do not know whether they are commutative or not, so I have to write separately AB in plus BA. If it is commutative, then it will automatically become 2AB. Similarly, if it is A minus B whole square, so just understand it this way, that if you don't want to remember the formulas, you just need to do this: A minus B into A minus B, very simply. Do not just change the orders. So for orders, that what I mean, A into A will be A square. This will be BA because B is preceding A. So just keep it B and do not confuse it with AB. This will be what? Minus AB. And this will be minus minus plus B square. So this is the formula that you will get. So do not interfere with this formula. You cannot write this as minus 2AB. Remember. Similarly, A plus B into A minus B. Just do not quickly go over and write that it is A square minus B square in terms of matrices, right? Now you got the point. You just have to remember the key formula over here, which is here. Similarly, the other two formulas can be remembered. So A into minus B is nothing but you can take the minus here or you can take the minus outside. That's not a problem. That's acceptable. Okay. The other properties that we have to do is the power of matrices. So first of all, we only talk about positive integral power. So something of the sort where A is a matrix and you say A raised to power minus 3. So this is not it's absurd. So in fact, we'll do it later. What do you mean by this? Is nothing but you have tried to find the inverse and you have taken the cube of the inverse. This is what is meant, but it does not mean that A is raised to power minus 1 by 3. So if I say A is raised to power k, first of all, remember k has to take place of a natural number, right? We cannot have fractional powers of the matrix. Okay, the other stuff. So if it is am raised to power an, so yes, this is something very normal which you do in algebra, that is a raised to power m plus n. So powers actually work as if you are working in algebra. Another interesting property for identity matrix is that whatever power of identity matrix you raise, you will again get the identity matrix back. So I raised to power k is nothing but I, and if you take power 0 of any matrix, then yes, this is something which you should remember. You will get identity matrix of the same order as that of A, that is in, where I am assuming that the order of A is nothing but order of A is equal to n. When let's quickly talk about the questions of matrix multiplication. So A is given, and this is a normal polynomial that is given to you, right? Now you are asked to find that f A is equal to 0, where you are going to put A in this polynomial. So this actually converts it to matrix polynomial. That's it. So one important thing that I'm going to talk about here is, I am talking about matrix polynomial. So when you put fa, so this becomes a square minus 4a. That's not a problem. But yes, 7 will not be 7 anymore. It will be converted to 7i. That is the 7 times identity matrix that you people have to remember. So whenever there is 1 in the polynomial, the corresponding matrix polynomial counterpart will be identity matrix, right? Now you can solve this. I am leaving that solving part for you because it's really simple. What you have to do for a square is nothing but you will do multiplication of these two, right? So multiplication, I'm sure you people can do. I'm much more interested in the other half. Use this result to find the value of a5. This is a board level problem. You need to find a raised to power 5, and you do not need to find a raised to power 5 by doing this particular step, that is a multiplied by 5 times. They have not asked you by this method. So what we have to use here is that you already know that if a is a root of this particular equation, so that means a square minus 4a plus 7i is equal to 0. This is what we know, right? From here, what I can say that value of a square comes out to be 4a minus 7i. This is what I know about a square. So now, even before going for a5, we first of all have to find a cube, because without that we will not be able to find a raised to power 5. So what is a cube? A cube is nothing but a into a square. And now we know the value of a square. So a square is nothing but 4a minus 7i, which gives you the value as 4a square, right, minus 7a. A into I is nothing but a. Use the value of a square again here. So if you put the value of a square here, you will get what? 4a minus 7i minus 7a. And if you do the calculation, this 16 minus 7, which will give you 9. So this becomes 9a minus 28i. Right. So if you notice, what has happened is a cube can be calculated in terms of a only. Similarly, if you want to find a raised to power 4, then what you will do? A into a cube. We have got the value of a cube, which is this. So you will get 9a square minus 28a as the answer. Again, do the same stuff. Put the value of a square again here. So it will be something like this, right? Minus 28a. So 9 into 4, 36. 36 minus 28 will be nothing but 8a, and this will be minus 63i. Then the last step would be to solve a raised to power 5, a into a raised to power 4. So this is how you are going to solve. I'm leaving this now to you people, how you are going to do it ahead. All right. So the beauty of this problem is that you will never have to multiply again and again. You can just solve this in terms of a and identity matrix. Okay, so the next problem is you have to find the value of this, where omega and omega square are basically cube roots of unity, right? This is what we did in complex numbers. So for cube roots of unity, we know the formula that 1 plus omega square is equal to 0, and we know that omega cube is nothing but equal to 1. This is the formula that we are going to use for multiplication of this particular matrix. So first of all, this is normal addition, right? And then you will do multiplication. So yes, already the first step is to add them up. So if you add them up, what will be the matrix? Let's say 1 plus omega, then omega plus omega square, then it will be omega square plus 1, right? Something like this, and omega plus omega square plus 1. I am leaving the other then for you. You just solve it. Okay, so what are those values then? So if we talk about the values, 1 plus omega is nothing but minus omega square. Let's see this from here. Omega plus omega square is minus 1, omega square plus, so you can just write all these values in terms of a single variable, right? So all will be minus. First of all, you can see this. So all of them is minus. So we can take the minus sign common, and then you need to multiply. So this actually results in this kind of stuff, right? 1 omega, and this will be 1 omega square, omega and omega square. This is what is left with you. Now we want to multiply this with the remaining, that is 1 omega and omega square. Now let's first of all, before multiplication, check whether they are in the form of multiplication or not. This is 3 cross 3 and this is 3 cross 1. Yes, they are multiplicable, and the resultant would be a 3 cross 1 matrix. So that means 3 rows and 1 column. So let's start the value. So it will be omega square plus omega cube. So omega cube is nothing but 1, right? So this becomes omega square plus omega plus 1, which is nothing but 0, right? This is 1 plus omega, right? omega square, sorry, this will be omega raised to power 4. So how do you solve omega raised to power 4? We have done this, so divide this by 3, the net remainder is the net power. So if you divide this by 3, remainder is 1, so it will be nothing but 1. So again this becomes 0, and the last will be omega plus omega square plus omega raised to power 4, which is again what you will get. Okay, so there is some error. We need to find the error somewhere. There we have committed a mistake. Yes, this is my bad. This is minus 1. Why? Because you can see very clearly this is omega plus omega square. So this will be minus 1. So this will be 1. So here what you will get is not omega. Yes, you will get something of 1. Then only the answer null matrix will come along. So my bad. Okay, yeah. So this is 1. So this is 0, which is nothing. So that means the answer we were looking for is the null matrix, right? So this question was particularly taken only just to make sure that you remember and revise the concept of cube roots of unity. Next problem is that you have a 2 cross 2 matrix, something like 2 pi by 7. So I assume theta is 2 pi by 7, right? For what value of k this will become identity matrix, that how many times we multiply this so that this becomes identity matrix. So A is something like this: cos theta minus sine theta, and this is again cos theta. So something of this sort. Okay, now before we go further, can you say when this will become 1? So before we go, so let's see, you want 1, so this particular component should be 1. So let's say cos phi is equal to 1. When does this happen? So this implies that theta should be equal to 0, or it should be equal to 2 pi. Compare this. So this sine minus sine phi should be equal to 0 for some matrix. So this happens when theta is again equal to 0 or 2 pi. So if you notice, that means the angle phi should be, or we can say 2 pi here. So when this theta becomes 2 pi, that is the target. Here theta is 2 pi by 7. So this gives a hint that the value of k that we want to attain is something which will make this 2 pi. This is the hint given in this question. So if I start doing this, let's say a, and if I have to calculate a square, so what will be the value of a square? It will be, let's just simply calculate it. So this is what will be the value of a square, and if you simply see, the value of a square will nothing but this becomes cos 2 theta, this becomes minus sine 2 theta, right? And then this will become what? Sine 2 theta, and this will be again cos 2 theta. So if you see that what has happened with a square, so a square has converted into where the value of power gets into the angle, right? So then we can generalize this, that if a raised to power k is there, what is going to occur is that you will get cos k theta minus sine k theta, this will be sine k theta, and this will be cos k theta, right? This is what we can assume. We wanted the value of k theta now to be 2 pi. Now what is the value of theta here? Theta is originally was 2 pi by 7. This comes out to be 2 pi. The value of k that you will get here is nothing but 7. This is the answer we were looking for. So k has to be 7 for this particular question to be true. Now let's take the other problem. It says you have to find the value of this. So this particular symbol here is the capital, you can say value of pi, right? But it does not mean pi. So if something of this is given, so you remember summation is basically for sum, and this is nothing but it is taken for product, right? So that means you want to put different values of r here, and then you are asked to find their product. So for example, this is nothing but you can understand it in this way, that a1 a2 a3 up till a50, that is what you will get by putting this. Let me assume that if this is ar, so you have to multiply all of them and then find the answer, right? So if we start with a1 into a2, what value you will get is, so a1 is nothing but 1 0 1 1. What will be a2? A2 will be 1 0 3 1, right? This is what you will obtain. So let's start multiplying this. So if you multiply, what you will get here, the first element will be 1. The next element that you are going to get is 3 plus 1, the next element will be again 0 and the next element again will be 1. So if you notice what has happened here, the pattern that I am trying to see, that the three elements remain the same. Which three elements? Yes, so this element and this element remain the same, whereas this element, what has happened to this element is it has added these two. Okay, so now if I multiply this with again, let's say A3, so A3 is nothing but 1 0. Now A3 will be 5, right? Just put the value of r equal to 3 here. So now what will happen here? Can you see? Again this will become 1, this will be 0, this will be 1, this will be 5 plus 3 plus 1. So yes, now I have got a pattern. So if I wanted to find the product of r goes from 1 to 50, this will be just equivalent to saying 1 0, and this will be what will be the value of when you put r equal to 50 here, that will come out to be 99. So this will be 99, 97, sum of first 50 odd natural numbers. This will go till 1 and this is 1 here. So this is the answer that we were looking for. This completely reduces to sum of first 50. So this is what? Summation of first 50 odd natural numbers. That's it. Okay. How do you find the sum of this? Okay, so please remember, if I again want you people to remember that sum of first n or n odd natural numbers, right? N odd natural numbers is nothing but n square. Please remember, this is something very important. So n here was 50, so the sum will be nothing but 2500. So the answer that you're going to mark in the exam is something of this sort. So this is the answer that we were looking for. Okay. Okay, now let's take a question based on trace. So A, B, and C are three matrices which are given to you. You need to find the value of the trace of A, then trace of ABC by 2, trace of A into B square, BC square by 4, and so on. And this process goes till infinity. So what is the trace of A first of all? So trace of A is nothing but the sum of its diagonal elements, which is 2 plus 1, which is nothing but 3. Then the next element that you people have to do is you have to find trace of A, B, and C divided by 2. This is what you people need to do. For this, the formula that you people can remember is, if it is divided by 2, that can be taken common, and you just need to find trace of A, B, and C. So the formula that you can remember is trace of lambda times A is nothing but, you can take the lambda outside and you can just find the trace of A, which is completely very obvious property. Even you can just do it orally. Okay, so now coming back to the question, you need to find A, B, C. So let's first of all try and find what is the value of BC, because again, why I'm trying to find not AB first but BC, because again you have to do BC square. So BC is let's see what will be the BC. So BC will be this product, and they are completely comparable as in terms of multiplication, right? This is what it is. So this is what is the value of BC, and interestingly this comes out to be the identity matrix. So if I say A, B, C, this is nothing but A only, and if I say A into B C square, this is again you can say is A, and if this process goes on, so that means if I do the cube also, then always the answer will remain A, because this is identity matrix. Identity, we know that I raised to power n is nothing but again I. So the question then is nothing but you are asked to find trace of A plus 1 by 2 trace again A, then you are asked to find 1 by 4 again trace A, and this process then continues till infinity, which we can now very easily solve. Why? Because trace A comes out to be common. What is left is 1 plus 1 by 2 plus 1 by 4, which is nothing but a infinite GP. Okay, so trace of A is nothing but 3, which we know, and this is how you can calculate this is that sum of infinity is nothing but A upon 1 minus R. A is 1, this is 1 by 1 by 2, this gives you answer 2. So the answer to this particular problem is 6. That is what we were trying to figure it out. And let's take the other concept of this chapter, that is transpose of a matrix. So transpose is nothing when you actually interchange rows and columns. So it's basically the called the transpose, right? You replace columns and this. So for example, if I have to explain, it is A, B, C, 1, 2, 3, and D, E, F, right? This is a 3 cross 3 matrix, and if you say this is A, so first of all the A transpose is written by A T, right? Something like this. So the first column here is A1D, this becomes your first row, very important. Then the second column will become your second row, and the third column will then become your third row, as pretty straightforward. Again, the order here is 3 cross 3 because the m and n are equal. So if A has the order of m cross n, then the A transpose obviously will then have order n cross m, though the number of elements will remain same. The properties that we will have to remember is if you take 2 times the transpose, you will again get back to A in algebra. So if it is A plus B and then it is asked that you transpose it, it is equivalent to saying that you transpose individually and then add. But this property is not valid when you are in multiplication. So AB transpose, that is when you are first asked to multiply them, the order gets reversed. You have to do this, that B transpose into A transpose, and this property can be applied for n number of elements. So for example, if there were 3 elements A, B, C transpose, what you will say, C transpose into B transpose into A transpose. This is what you have to say. So K times A transpose, now here K is a scalar quantity. So for scalar, nothing has to be done, just take the K outside. Transpose of identity matrix is again I, very important stuff, and the trace of the matrix and its transpose are actually same. Why? Because in the, if you notice that here, what were the diagonal elements? To A to F. In transpose, again they are A to F. So actually the diagonal elements does not change, very simply. And if you want to talk about mathematically, so if Aij was there, actually this will be, so Bij, where B is representing the transpose, will be nothing but Aj, right? So you will swap them. This is how mathematically this is being written. So if something of this sort is written, just understand that B is nothing but A transpose. Okay. Now let's take a very good question on based on transpose, which was being asked at IIT JEE advanced level, but I'm taking it here because this might be asked. This is my prediction that it might be asked because it's not that tough to understand. So P looks like a very intimidating matrix. It's a huge one. Let's just keep it simple that it is a 2 cross 2 matrix. I is given to be something of this, where this I is basically nothing but let me assume that this is iota, right? This is I, here is iota. So and Q matrix is defined as P transpose multiplied by A into P again, and you are asked to find this particular value, which is something again huge, P into Q raised to power 2010 into P transpose. This is what we have to find. This is the required stuff. Okay, so before even going further, I know that you people who have not attempted these kind of questions will be thinking how to go about this. So whenever I have already I have already told you that whenever the question looks big, try to fragment into small parts. So how small parts are going to be done, let's see. Can I say PQ into Q raised to power 2009 P raised to power T? Now you know the value of Q from here, just put the value of Q again. So what you are going to get here, let's see, this Q, right, will be what? P transpose A P Q 2009 P transpose. And if interestingly, I don't know whether you can see it or not, it looks like even if you have even further made this question big, but no, you have actually reduced the question. Why? See this pattern. Earlier you started from when the power was 2010. Now exact same stuff is there, but the power is being reduced by 1. It is basically recursive, or it is getting reiterated. You just need to solve this particular component which is lies ahead of it. So here ahead I can say it is P into P transpose into A. Now let's just focus our energy on P into P transpose, right? So what we have to find is P into P transpose. I'm leaving this part for you guys to solve. What is P into P transpose? You know that what is the value of P transpose, where you will multiply by shifting the columns. And interestingly, what you will find that P into P transpose will come to be identity matrix. So the huge problem which you think it was so huge has actually reduced to a very simple problem, because now it reduces to A. This becomes A into P raised to power Q 2009 P raised to power transpose, right? So now what has happened is when Q was simplified once, A comes out once. So simply you can say if I again reduce q, so the next step would be doing this. You know the pattern, right? So what will happen now? Can you tell me? What will actually transpire here is that A will go on something doing the same step again and again, again and again, right? This will be what 2007. So what will be the last step here? Last step, can you tell me? So for last step, let's see if we get to this particular step where it is 2000, let's say 9, what you will be left with? P, Q, P transpose, right? This is the last step that you will obtain, and what will you obtain here is 2009, right? P, what is the value of Q? P transpose A into P transpose. So P into P transpose is identity matrix, then P into P transpose will also be identity matrix. So this actually then converts to A raised to power 2010. That's it. So this complete huge figure gets converted to A raised to power 2010, and since A is basically a diagonal matrix, so we know that A is being a diagonal matrix where both the diagonal elements are I. So the property of again a diagonal matrix that you can remember is if you raise the power k, then for diagonal matrix you don't have to do anything, just raise the power for the diagonal elements, all the other elements will be 0. So A raised to power 2010, right, will be nothing but diagonal of iota raised to power 2010, iota raised to power 2010. And we know that what is the value of iota raised to power 2010? Can you tell me? Yes, it is nothing but iota square. This will reduce to iota square, which is -1 and -1. So diagonal -1 and -1 will be something like this, which is nothing but -I. So the answer of this particular question that we were asked and IIT level is nothing but -I. So this is the problem. So let's talk about other two important concepts of this chapter, that is symmetric and skew-symmetric matrices. So symmetric matrix is a matrix where the diagonal acts as a mirror, right? So what I mean by diagonal acts as a mirror, that if you take Aij and the elements at Ji are equal, or in a way you can say A is equal to A transpose, then you call it a symmetric matrix. And whereas here in terms of skew-symmetric, what has to be done when A transpose comes out to be minus times A, then you will call this as A as a skew symmetric. So for example here Aj will be minus times Aij. This is the meaning. So I have taken an example here. So if you take AHG, BF, so you actually, this is the delta for second degree curve also. And if you take the transpose of this, so what will be the transpose here? Yes, you will again get AHG, HG. This becomes the second row. So second column becomes the second row, B, F, C, and this is again FC. So the transpose comes out to be same. That is why we are saying that it is symmetric matrix. For here, if you see in this particular question, right? So if you take a transpose, this minus will come here, this will come here, this minus goes here, this goes here. So A transpose is nothing but minus A transpose. That is why it is skew symmetric. Okay. So another important property of a skew symmetric is that trace of a skew symmetric matrix is always 0. Why? Because diagonal elements, what you can remember is that diagonal elements of skew symmetric matrix is always 0. How we can say this is that, let's say this is the formula by which we have already done, Aj is equal to minus Aij, right? And for diagonals we know that I is equal to j. So this is Aii is equal to minus Aii, and if you solve this, this returns what? 2Aii is equal to 0. That implies Aii is nothing but equal to 0. So very important stuff. For that a skew symmetric matrix, the diagonal elements must be 0. Also, if we talk about the properties, so if A is already a symmetric matrix, then minus A, K times A raised to power transpose, or A raised to power n. So all of them, or in fact the inverse, which we are going to study later, so they all will be symmetric. So for a symmetric matrix, all of them are symmetric again, right? So, but in case of skew symmetric, if A comes out to be skew symmetric, then you have to be very careful. A raised to power 2n will be symmetric, whereas A raised to power odd power will be skew symmetric. And K raised to power, where K is a real number, you can say a scalar, so this will still remain the skew symmetric. Whereas for symmetric, So the important stuff is a raised to power n in symmetric will always be symmetric, vice versa. But in case of a being skew symmetric, you have to check what power it is. So if it is a even power, so even power will convert a skew symmetric to simply symmetric matrix, right? This is what you have to remember. Let's take a very different problem on symmetric and skew symmetric apart from what you people do at your board level. It says how many distinct entries or the maximum number of distinct entries are there in a symmetric matrix of order n, right? So let us first of all take a symmetric matrix of order 3 cross 3 to understand this particular question. So as we have already taken, it is AHG, HG here, B, F, so F will come here, and C. So now why I've taken this question is, again, it's a beautiful PNC problem and a huge concept. Here the concept is that diagonal acts as a mirror line. So it acts as a mirror, or you can say a line mirror. Why a line mirror? Now I'll tell you the concept. So if you take this as the line mirror, right? Okay, let me call this as the line mirror. You can say that image of H is here, image of G is here, and image of F is here. So that means if you want to select diagonal skew or let's say a symmetric matrix, what you are required is just to find out upper triangular matrix, right? Because you just need to figure out the upper triangular matrix, because the lower triangular matrix is nothing but reflection of the upper triangular. So the reflection of this will give you lower triangular matrix, right? So the number of distinct entries will come from significantly from the only this portion, right? So the distinct entries will come from here, right? This and this particular region, whereas the remaining, the below ones, will be nothing but repeated components, as I have shown you earlier. So they are the images, right? So the concept we have already done. So now the only the part is left is to solve. So if let's say it is n cross n, so for n cross n, what will happen is, let's say it is a1, a2 and a3, and it goes till nth term here, right? This will be b1, this will be b2, and this will be b3. This goes till again bn, right? And it's going like this. So we know that these n, and if we talk about the first row, then right, in first row, how many distinct entries are there in the first row? It is n, right? But if we talk about the second row now, in the second row there will not be n distinct. Why? Because a2 and b1 will be the mirror images of each other, right? So this will be n minus 1 entries in the second. Similarly, c1, c2, c3, and we still go on till this. So what will happen now? Just imagine that this is your mirror. This is your mirror. If this is the mirror, then C1 will be similar to something like this, A3, and C2 will be then similar to, again, what? Somewhere here, B3, right? Just imagine here. So the only different elements now you will have is n minus 2, and in the last, if I go till n, so if I complete the line mirror, so in the last row only one element will be distinct, which is this element itself. So the number of distinct entities is nothing but 1 plus it should be 2, right? Now I hope you have got the point. So it will be 1 plus 2 plus 3 up till nothing but n. So this is sum of n natural numbers, which is nothing but n into n plus 1 by 2. So these are the maximum number of distinct entries that you can have in a symmetric matrix, right? And why we are saying a maximum number? Because the elements a2 and a3 can also be same, right? So but we are taking that all the elements in the upper triangular matrix are distinct. That is why we are calling maximum. Otherwise it could be less than this number also. Well, let's take the determinant of matrix. So though we are not getting into determinants, it's just to so that we can understand the concept of inverse and adjoints. So we know how to solve determinant. I'm not getting into details. I'm just interested in properties of the determinant at this point of time. So AB determinant is if you have multiplication of matrices and then you are taking the determinant, you can take the determinant first and then multiply all the determinant. This is valid for n number of matrices. transpose determinant is nothing but equal to determinant of the actual matrix. Very important property is that if you have k times a matrix, right, and then you are going for determinant, remember then the answer is not equal to k times determinant. This is what I have seen the error committed by most of the students. It is equal to k raised to power n times the determinant, where n is nothing but the order of the square matrix. So, and also remember that the determinants is only valid for your square matrices. So n times the k will come out. Why? It is the basic distinguishing is that here k will be multiplied with each element of the matrix. When taking common, in determinants we take common row wise. So k will come common n times because it will be present in n rows. So that is the reason it will be coming n times outside. Okay, if a and b are of the same order, then a b determinant is equal to b a determinant, which we can prove it simply from here, right? If it is a skew-symmetric, very important property, if it's a skew-symmetric matrix of order odd order, right? So the answer to its determinant is 0, right? You can remember this. I have seen that in bit set this has been asked straight away. So this concept rather than a formula was being asked. So if diagonal matrix is there and you are asked it's so we know that diagonal matrix is written something like this. Let's say it's a 3 cross 3 diagonal matrix, and if you are asked to find the determinant of this A, it is nothing but A1 into A2 into A3, very simply. And if you are asked to find the power of the determinant, you can do it anyway. You can take the n inside or you can take the n outside, doesn't matter. We have already done this. This comes from the proof of this particular again. Another important term is the singular and the non-singular matrices. So singular is something where the determinant is 0, non-singular is where the determinant is non-zero. Okay, let's apply them in the questions. So now let's take a concept that is adjoint, which is important from your board's perspective because it's asked there. So let's say we have a matrix 3 cross 3 matrix, which I have taken like this: A, B, C, D, E, F, G, H, I. So before we try and find the adjoint, let's say this is the A matrix, right? You want to find adjoint, so this is written like ADJ, adjoint A, right? So first of all, things is we have to understand is minors and cofactors, right? This is important. Why? Because it is being asked at your boards. That is why I am taking this forward. Minors and cofactors. So minor of A11. So this is the A11 element, right? So minor of this is written as M11, which is nothing but leave this row and column and write the elements in the determinant. EF HI, right? Then if I have to find the minor of A21 element, A21, similarly you can say A21 element is this element, leave this row and column. What you are left with B, C, H, I, and so on. You can find co-minors of all these respective elements. What we have to find is actually the cofactor. So if this is the co-minor, what is the cofactor? C11 is written as the cofactor, which is nothing but minus 1 raised to power 1 plus 1, that is add these two, and nothing but M11. Similarly, this will be what? C21 will be minus 1 raised to power 2 plus 1 raised to power. So if I ask Cij, so Cij is nothing but minus 1 raised to power what? I plus j Mij, right? Mij. This is the formula for cofactors. So what is adjoint? So adjoint of a matrix is nothing but transpose of the cofactor matrix. So cofactor matrix is what? It is the cofactor matrix. Let's see. C12, C13, C21, C22, C23, C31, C32, and C33. And if you take the transpose of this will now give you the adjoint. Okay, so this is how you have to find adjoint if it comes in your board exam. You need to find all the 9 cofactors and then you will form the cofactor matrix and then you will take the transpose. So this particular matrix over here, this one, right? This is known as cofactor matrix. Cofactor matrix. Okay. Now coming to the properties, very interesting property that you people should remember, that if you multiply A11 with C11 plus A12 C12 plus A13 C13, the answer that you will get is determinant of the A matrix. That means if you multiply the elements of a row with their respective cofactors, you will get the determinant. But if you say A11 is multiplied by the cofactors of the other rows, that is the second row, let's say this will be C22 and this is A13 now multiplied by C23, the answer will be 0. Similarly, I can say A11 C31, this will be A12 C32 plus C A13 C33, this answer will also be 0. Please remember, this is very important stuff. Okay. Okay, now let's take the properties of adjoint. So the basic property that you will have to remember is A into adjoint A is nothing but determinant A times identity matrix, right? This is the basic property that is very crucial, and using this all the other remaining properties are being proved. So if somebody asks you the determinant of adjoint A, this will be nothing but determinant A raised to power n minus 1, where n is the order of the n belongs to the basically n is order of A. Okay, this is what is meant here. The third important property is adjoint of adjoint A something. So this is determinant of A raised to power n minus 2 times A. Determinant of adjoint A is nothing but determinant A n minus 1 square. So these two properties we can prove, but the remaining ones that are there, you just have to learn them. So adjoint of A transpose is nothing but adjoint A transpose. Adjoint AB is nothing but adjoint B into adjoint A. Then adjoint of A raised to power M is nothing but adjoint A raised to power M. Ka is nothing but K comes out to be n minus 1 times ahead, and this is the property. So let's just first of all start and prove this particular property here. So you know that what is adjoint A? Adjoint is nothing but transpose of the cofactor matrix. So this was your C1, C2, C3, C21, C22, C23, and this is C31, C32, C33, and you were to take the transpose of this, right? Now let's see. So we want to prove that the determinant of this is nothing but this particular stuff here. So let's see how we are going to do this. We have the major property that A into adjoint A is equal to this here. Let's take determinant on both sides, and why I'm taking this particular question, I'll make sure that you understand that, and it's really very interesting to solve. So this is this, and I can split the determinant. Now I cannot do something. So if I've seen students writing something like this straight away, which is not true. This is not true. Why this is not true? This is a scalar. So scalar will come outside the determinant. So scalar comes outside the determinant by the time of the order it is. So if the order of this is n, so determinant A will come outside not just once, it will come outside n times, and then you will write something like this. So this is the reason that I'm taking this proof. This is very important step here. So now if you see, this becomes nothing but adjoint of A is nothing but simply solved, because we know that this is equal to 1, and hence the property is being proved. Now let's take the other proof. We want to prove this particular step here, and for this again I'll start the question from the basic theorem, that is A into adjoint A is determinant A into IN. Now you want adjoint of adjoint A. Here it is only adjoint. So now let me replace here to a substitution that I replace A by adjoint A, right? Since this is an identity, I can replace any value of A. So this now question then reduces to what? So this will now become adjoint A into adjoint of adjoint A. So this is what you wanted, which has actually arrived here. But yes, now it has become a bit complicated. Why? Because this is now the target of the question. We just proved that adjoint A is nothing but determinant A raised to power n minus 1, where n is the order of the A. Now this is up till now you have got this. Now the only stuff that you need to remove is basically this particular thing here, which is right in front of this. Otherwise, this question is this is the required stuff, right? This is what you want to find. So how this can be removed is again by taking the same formula, that is a. So I always told you that this is the major formula which you have to focus on. So let's pre-multiply everything by a. So a into adjoint a. So what this will become is, yes, determinant a into I into, you can say, adjoint of adjoint a, right? And what this would be a into I. So this is scalar, you can just shift it here. So this becomes determinant a raised to power n minus 1. A into I is nothing but a again. This and this gets cancelled out, and I into is this again. So that is why you get the formula adjoint of a is nothing but determinant a n minus 2 times a matrix again. So this is the formula, and hence it has been proved. Okay, and if you want to prove that, what if I take the again the determinant of adjoint a, what will happen? So if I take the determinant again, so determinant will be taken on this side also, right? So this is something like this. Remember, this is a scalar, it will come outside of the determinant how many times? Not just once, it will come, yes, n times it will come outside. So this will be this and this, and if you notice what this becomes, this completely becomes n square minus 2n, and this power will also be added, which is 1, and this completely reduces to determinant a n minus 1 whole square, which is the other formula that we generally use. So we have proved it actually here. Okay. Okay, let's take a question which is being generally asked of adjoint. It says adjoint of P is this, so adjoint P is given to you, right? And you are asked to find the value of determinant of P. Now you can simply solve this. Why? Because we know the formula that adjoint of P determinant is nothing but determinant of P raised to power n minus 1. Since n is nothing but 3 here, why I can say 3? Because the order of P and the order of the adjoint of the P will be same. So you know this, it is nothing but adjoint P is nothing but, this is P square. Now you can easily calculate this, just find it and under root that stuff to get the value of P. So I'm leaving the calculation part for you, which you can solve easily. And let's take the other concept, which is inverse of a matrix. So what do you mean by inverse of a matrix? Is that if you have a matrix A and B, such that if you multiply them and you get a identity matrix, or you do BA, right, in whichever way, and you get I, then A is known as inverse of B, or B is known as the inverse of A in vice versa form. So I can say B is nothing here but A inverse, and it is written something like power minus 1. So this is the concept of inverse. Or in fact, if you want to find the formula, so this is the formula where A inverse is nothing but inverse of a matrix is found using its adjoint. So adjoint A divided by determinant A. Obviously here you can see that determinant A should not be equal to 0. That means A should be yes. So you can say that the inverse of a matrix exists for only for non-singular matrix. That is basically the major criteria of finding the inverse. Okay. Quickly coming to the properties of inverse. So transpose inverse is nothing but inverse and then transpose. As we did in the case of transpose, if you have A, B and C multiplied and then asked its inverse, it is equivalent to saying inverse individually but in a reverse order, right? Okay, and this could be used for n number of times. If it is A raised to power k and then inverse, it's up to you whether you can find the inverse first and then take the power, completely up to you. Similarly, adjoint inverse is nothing but take the adjoint of normal and then inverse. A inverse will again give you A. Determinant of A inverse, something interesting, is nothing but 1 by A. So this is something interesting because it's fairly very simple, but people do miss out. And if A is a diagonal matrix, so if A is a diagonal matrix where A1, A2 and let's say A3, right, 3 cross 3, and we want to find A inverse, interestingly A inverse is nothing but 1 by A1, 1 by A2 and 1 by A3. Very interesting property in terms of diagonal matrices. Okay. So let's see how inverse is being asked at entrance exam. I am leaving that part of board level preparation for you where you are asked to find inverse. You can just find the adjoint and divide it by the determinant. Okay, so you can do it on your own. So if we talk about the objective type question, so let's say B is given as minus A inverse BA, and you are asked to find A plus B whole square. What will be the value? We know that A plus B whole square is nothing but A square plus B square plus AB plus BA, right? This is the stuff which we know, which is nowhere in the question, right? So we have to use somewhere here also, and we need to solve AB and BA. This is the major hustle in this question. So let's solve this by pre-multiplying with A. If I pre-multiply with A, so this is something can be written like this, right? And if I see what is A into A inverse, this is nothing but identity matrix. So this becomes what? Minus BA. So AB comes out to be minus BA, and if you just put this value over here, so this nothing but reduces to A square plus B square, which is your answer. That is B option. Okay. So simple problems are being asked at entrance examinations in regard to the inverse. Let's take another problem. Next problem says that A cube is nothing but a null matrix. Okay, it is not zero in terms of matrices, it is null matrix. So you need to find the value of this particular stuff, which I have now taken as P. Now you need to find the value of this here. Okay, this is the question. Sorry, this is not A cube, it is A square, which is there in the question. Let me rewrite. Yeah. So how do you solve this kind of question when nothing is clear what to solve? Now somewhere down the line we have to use P, that is A cube. So what I did, I multiply it with A on both sides just to introduce A cube. So I into A is A, this is A square, and this is A cube. A cube is nothing but 0. So this reduces to A plus A square. Null matrix cannot be added because A plus null matrix is A itself. So now we have A plus A square, but I also know the value of A plus A square from here, right? So what is the value of A plus A square? A plus A square is nothing but P minus I. Just put the value here, so it becomes what? P minus I, and you were asked to find the value of P, so it is I is equal to P minus PA, or I can say P is equal to I minus A. If you take common, you just do not write 1 here, it is I. So this says P into this matrix is I, so that means P is inverse of I minus A. Then only you are getting identity matrix. So the answer to the required problem is I minus A inverse, which is option B. Okay. Alright, so let's take the third problem. It says that if B is non-singular matrix, then find determinant. So this something is just an oral problem. Alright, so this is actually equivalent to this. And we know that they can be now splitted and be written like this, right? And we know the inverse, determinant of an inverse is nothing but the reciprocal. So this reduces to nothing but determinant A. That's it. That's the answer. Now let's take the other concept of this chapter, which is system of simultaneous linear equations, and how do you want to solve this. So this is the system of simultaneous linear equation which is given to you. That is 3 variables are given and there are 3 equations and you want to solve them. So how we are going to take this question is that we form 3 different matrices. That is the A matrix, which is nothing but matrices of the coefficients that you have for x, y and z in the 3 different equations. So this is represented by A, right? Then we take as the x matrix, which is the variables. X, y and z are the variables, and B is nothing but the answers that your outputs that you are getting on the right hand side, D1, D2 and D3. So if you notice, I can write this completely in the form Ax is equal to B. This question then converts to a matrix problem, right? Ax is equal to B, and you want to find the values of x, y and z. Now see Ax, so this is what, 3 cross 3 and this is 3 cross 1. So they are completely they can be multiplied and the resultant will be 3 cross 1, which is here. So you can check it out. So how do we solve this is multiply A inverse on both sides. So you will get X is equal to A inverse B. You know, the value of A inverse is to be found like adjoint A by determinant A into B. So this is how you actually get the values of X, Y, and Z. So, but how do you distinguish the characteristics of these equations? Let's see now. So I somehow take this into two particular concepts, right? One is the non-homogeneous equations, right, which you people have learned, and I'm telling you how to draw the diagram so that you can remember this properly. So when you call this non-homogeneous is that B is not a null matrix. Zero, it is not zero, it is not a null matrix. So that means D1, D2, and D3 are all not zero. One of them might be zero, but all of them are not zero. Otherwise, it will become a null matrix. Okay, if it is non-homogeneous, then what will happen? So for non-homogeneous, there could be two further categories. That is, let's see, I am going to tell you how. So here, can you see in the denominator what you are having is determinant A. On the basis of this, you will have two different categories. What are the two different categories that we have is that this is not equal to 0. That is non-singular matrix, right? If you have a non-singular matrix, then you have a unique answer. Don't worry about it. You will have unique answer. That means you will have different values of distinct values of X, Y, and Z here, right? But if it comes out to be the case that this is equal to 0, okay, then we have to think of two different cases now. So what will happen here is that if this determinant is 0, just think of the limit concept. I told you that when limit is 0 by 0 form, we can have a finite answer. So if this is 0, what is the numerator? It is adjoint A into B. And if this is also null matrix, then what you will say? 0 by 0 form, yes, you will have answers, but now you will have infinite answers. That's the answer you will give. You will have infinite answers this time round. But if you say that, sir, this adjoint A into B is not a null matrix, then what the answer would be? No solution. You will say the answer is no solution. You cannot have any value of X, Y, and Z which will simultaneously satisfy all of this. So this is the flow for non-homogeneous. Okay, and also important stuff that you people have to remember here is that this is called consistent, right? There are two words, consistent and non-consistent. So this is consistent with unique solution, and this is called consistent with infinite solution, whereas this is called inconsistent. When you cannot find a solution, this is called inconsistent or no solution, right? Let's talk about the other aspect here, that is homogeneous. So now you have something homogeneous. So for homogeneous, what will happen? We did that B is here non-zero matrix, so it will be now a null matrix. That means D1 equal to D2 equal to D3. All of them are at the same time 0. Now again here two cases will be there, right, depending on the value of determinant A. Okay, so if determinant A comes out to be 0, so if determinant A comes out to be 0, what we say here is that it will have infinite solutions. It will have infinite solutions. Okay, and if you say that determinant A is not equal to 0, then what we will say? Yes, there will be solutions, but only trivial solution is the answer. Only trivial solution. And mind it, I have used the word only. I'll explain why. And first of all, what do you mean by trivial solution? Trivial is, which is very obvious, that is X equal to Y equal to Z equal to 0. So this is called the trivial solution. Also understand that when we talk about homogeneous, there are either infinite solution or there is trivial solution. So homogeneous equations they are always consistent. You will not find a homogeneous equation which is inconsistent. They are always consistent. That means they will always give you the answer. Now the point is only whether they are infinite or they are trivial. Plus, if we talk about infinite, it also contains trivial solution, right? So whenever we talk about the trivial solution, or let's say a homogeneous equation, homogeneous always have trivial solutions, always. They always have the trivial solution as their answer. That is, what do you mean by trivial solution? That is x equal to y equal to z equal to 1. Because if RHS is 0, and if you put x equal to y equal to z equal to 0, this RHS will obviously become 0. Why I've taken this flow chart is, if you can just understand the flow of this diagram, every question on system of linear equations can be solved. Because I've seen that people are not able to remember all these 5 cases. So there are in total 5 cases, and this flow can actually be learned very quickly. So just go through the flow once again and be sure of that now you're clear of system of linear equations. Let us take a question to understand this concept. It says if trivial solution is the only solution of the equations which are given as this x minus ky plus z equal to 0, kx plus 3y minus k equal to 0, and the third one is 3x plus y minus z equal to 0. So you can see the values of d1, d2, d3 are 0. So this is a question based on homogeneous equation, and that is why obviously the trivial word is used for trivial. So homogeneous to have only trivial solution, right? Only trivial solution. We just did that determinant A should be not 0, non-singular. So what is the value of A? A determinant or A matrix is 1 minus K 1, K 3 minus 1, and 3 1 minus 1. Now what you need to solve is nothing but that this the determinant should be non-zero. You need to find those values of x where this determinant is not equal to 0. Okay, so this is a mistake, that this is not k, this is kz. So this is kz. Let me just correct it. So yes, k here, right? And this is also minus k. Okay, and if you go ahead and solve this particular LHS, so you will get something of this sort, k square plus k minus 6. And now you want to solve this is not equal to 0. So how you will solve not equal to 0 is that you assume that it is equal to 0. Let's try and find out the values of k for which this becomes 0, right? And we know that the values of k which will satisfy this will be minus 3 and 2, right, for equal to 0. But you want it not equal to 0, so just do this step, that k will take all real values except these two values for which it becomes 0. So if you put the values of k except minus 3 and 2, this is going to give you only trivial solutions, right? So this is the answer that we should mark in the exam. Okay, now let's take the particular concept called elementary row transformations, finding inverse using elementary row or column transformations, and this is basically a 6-mark question that is being asked at your boards. So how do we start? So first of all, if it's a, you have to use a row transformations. So right, so row transformations, you have to start from A is equal to IA. This is how you have to start. And if you are going to use column transformation, right, so how you have to start is A is equal to AI, right? So whatever we are going to do is we'll convert. So target here is we use transformation to convert LHS into I, and for RHS what we'll do, we'll convert I into A inverse, which will be our answer, right? This is the target. I'm going to teach you row transformation here, which you can then apply for column transformation also at the same time, right? So for row transformation, what you have to remember first of all as a rule, which I teach generally to my kids, is something of this sort. So start from this element, make this 1 and this 0 and this 1, because you want to convert this into identity matrix, and then we'll follow this track, then G, then H, right? And then we'll focus on F, then we'll focus on C, then we'll focus on B, something like this, right? Again, we are coming back to E. So this is the order that we are going to follow here. If you can follow this order, then you can be rest assured that you do not have to spend your time thinking on what to do next, what to do next. So let's start. The first step that you want to do is that we want to make A as 1, right? And we need to start the question from that A is equal to IA, where we'll make changes to this A and this I, not to this particular A, right? So we want A as 1, that is the first element A here, right? It is 0. Now let us just see, we want, then what will we want? We want A to be 1 firstly, then we want D to be 0, and the third thing that we want is E is equal to 1 again, right? This is the order that we want to follow, right? And we can do this by a very simple transformation here. If you just replace row 1 with row 2, see here, if you just replace row 1 and row 2, all these three will be taken care of in a single step. So let's apply this here. So when you want to replace row 1 and row 2, what will happen? So this A will be 1, 2, 3, 0, 1, 2, 3, 1, 1, right? This is what we can say. And this what will become? So this I will change only the elements in the I, not in this right hand side A, remember, right? So transformation will be applied only to this particular component, and if you apply, so this will become 0, 1, 0, this will be 1, 0, 0, and this will be 0, 0, 1 times A, right? This is what is done. So now in a single transformation you have actually done three particular steps, that is A, D and E. So now your next target would be what? Your next target is to make G is equal to 0, right? So how you can make G 0? So this is 0. So yes, you will do R3 goes to R3 minus 3 R1, right? If you do this particular step here, what, let's see, will transpire. So if a general help, a method that which row has to be transformed is R3. So first of all, write all the other rows so that you are not doing any silly error with those steps. So on this side also, as well as on this side. 1, 0, 0, and this is A. Now apply this here. So this will be 3 minus this will be 0. That was the intended target. So this becomes what? Minus 5, and this will be what? 3 R3 minus this. So this will be what? Minus 8, and what value you will get here? Now let's see, 0. This will be minus 3. This will be again 0. Okay. Sorry, this will not be 0. This will be 1. Okay, now the next element that you want is that H should be 0. So now let's take H to be 0. For this H to be 0, what you will do, that you will say that R3 goes to R3 plus 5 times R1, R2, if I add this. So now let's do this also. What it will have an effect is 1, again I am writing those elements which will not be disturbed. So these two things will not be disturbed. Similarly here also 0, 1, 0, 1, 0, 0 will not be disturbed because we are just changing the row 3. So row 3 plus 5 times, so this will be 0. This will now be reduced to 0. What will this will be? Minus 8 plus 10, right? This will be 2. Now what will this become? This will be 5. This will be 5 times, so this will still remain minus 3, and this will be again 0 plus 1, that is, so up till now this is fine. Now H is 0. Now you want I to be 1. So how you can do this step? Think of it, it's a very easy step, right? Let me just remove this here because I need the space. So now the next target is that you want I to be 1. This could be simply achieved by dividing R3 by 2 because you already have 2 here and 0 here on both sides. So what you are going to achieve here is, let's see, 1, 2 and 3. Again I am writing the rows which will remain unchanged first, here as well as here. So this will be 0, 1, 0, 1, 0, 0, and now I'll write the third row. Third row will become what? 0, 0, 1, and this will be what? Yes, now this will be 5 by 2, minus 3 by 2, and this will be 1 by 2. So just keep a special care because now we are into denominators. So there are chances of getting silly errors. Okay, so slow your speed down because it's a 6 mark question that will come on the boards. So now I is completed. Now you want F. Now your target is to make F0. So now think of how you are going to make F0. So F0 has to be made in such a way that other elements that you have worked on does not change. So always use those rows who have been completely done with the transformation. So for example, this has been done. So I'll use this now. So I want this particular component. So I can say this is 2 times R3. Right? If I do this 2 times R3, what will then happen? Again, let's just quickly write down the rows which will not be impacted by any way in this. So this and this will not be impacted. Similarly here 0, 1, 0, 5 by 2, minus 3 by 2 and 1 by 2 will not be impacted. What will this become? 0, 0, and this will reduce to 0. Got it? And on the right hand side you will get minus 4, 3 and minus 1. Okay, now the next step that you people have to do is that C should be 0. How can you make C 0? So this 3 has to be 0. Again we'll use the row which has been used completely. So this is R1 minus 3 times R3, right? Because these two are 0, so they will not impact anyway. So now what is going to be changed is the row 1. So I'll not write row 1, I'll write row, this is not 0, this is 1. Let me just correct it. Okay, so now let's do the calculation. Then it will be what? R1 minus 3, 0, 0, 0. So this will remain 1 and this will remain 2. This will become what? 0. Now let's do the calculation here. So again we have to be very careful while doing the calculation, and respectively you will obtain the elements as minus 15 by 2, 11 by 2 and minus 3 by 2 on the other side, right? Now only the element left is B element. Now in the next step you want your B to be also 0. For B to be 0, what you will use, that R1 goes to R1 minus 2R2. And if you do this, the left hand side determinant will completely become identity matrix. That means your process is now complete. Whatever you will get on this particular side will be your answer. So we have already got 5 by 2, minus 3 by 2, and this is 1 by 2. This is minus 4, this is only 3, this is minus 1. Now just do the calculation over here. So this is R1 minus 2R2. So this will be minus 15 by 2 plus 4. So this will give you 1 by 2. 11 by 2 minus 9 by this will be what? Minus 6. So this will give you what? Minus 1 by 2. And this will be what? Yes, it will again give you 1 by 2. So the value of the inverse that we were looking to find is nothing but the matrix that you have obtained here. That is this particular matrix. So this particular matrix which has these elements is nothing but A inverse. So this was A inverse. And this is how you have to solve your question if it comes in the boards. Right, don't worry, this will not be asked at your competitive exam. Obviously you do not have time that much to solve this lengthy problem, but yes, this is something completely irrelevant for your board. So people who are not going to take board, that are the droppers, can completely skip this portion. Okay, so for column transformation you do have to do all those same steps, but just remember that do not use row transformation. There you will have to use column transformation, but the process will remain something similar. Okay, and if I have to tell you the trick for column transformation, so for column transformation, right, so for column transformation, so the order that we generally follow is we go from A, B to E, right, firstly. Then we'll start not from G, but we will start from C, F, I. This is the pattern that we follow there, right? So just remember the pattern, that in cases of row and column, the pattern just changes. Otherwise the concept generally remains the same. Okay, so by this we come to the end of this chapter, and again I repeat that this chapter is important because it is going to give you full 4 marks if the question comes into the exam, because the question is going to be easy. So please work on this chapter, and since this is also in the boards and it has good weightage in boards as well, so it becomes much more important from both the points, right? So as usual, I'll be sending the worksheets to solve the questions. You practice the NCERT. For NCERT, you can just go and check the video solutions if you are stuck up at any problem in a particular problem in a particular exercise, and just finish this topic. It is an easy topic. I could easily say that it could be finished in, let's say, 3 or 4 hours of time. Okay, so I see you with the other topic, that is determinants, day after the class. Good night. Keep working hard. Keep learning.